Hello everyone, I am Syed Hisham and today I will be presenting the chapter 2 of the rare earth element. So the chapter 2 answers the equally important questions complement to chapter 1. Where do rare earth elements actually come from in the ground and why does that matter for investors, analysts and policymakers? We start with rocks and end with strategic dependencies. Three statistics frame the challenge immediate. There are 17 rare earth elements. All commercial production flows from just four primary ore host types, and approximately 60% of the world's supply comes from a single nation. That concentration is not an accident of geology. It is the product of decades of deliberate industrial policy. By the end of this chapter, you will understand both the geological reasons why these elements are where they are and the political and regulatory reasons why so little of the world's enormous reserves have been converted into production outside China. There are four primary ore hosts that drive all commercial RE production. Bastnäsite is a fluorocarbonate mineral dominant in light rare earth. Monazite is a phosphate mineral, LRE bearing, but with critical complication of containing thorium. Xenotime is a yttrium phosphate mineral dominant in heavy rare earth, and Ion Adsorption Clay or IAC is weathered granite where REs have leached out and absorbed onto the clay particles in the soil over millions of years. Despite looking least impressive on paper, IAC is arguably the most strategically important source type in the world. Beyond the primary four secondary sources include red mud from aluminium processing, fly ash from coal power plants, coal mine waste, phosphogypsum from fertilizer manufacturing, legacy mine tailings, and e-waste including magnet scrap. These are covered in detail on slides 6 and 7. The key insight anchoring this chapter is that commercial viability is not determined by geology alone. Over 200 RE minerals exist in nature. Fewer than 10 are commercially viable, and just 4 ore types drive all production. The gap between that what exists in the ground and what can be economically extracted is enormous. And that gap is where most of the analytical work in this sector happens. Now we will talk about the global RE or geography. So geography is destiny. The distribution of rare earth deposits around the world is deeply unequal with profound commercial and geopolitical consequences. China dominates with IAC deposits in its southern province and the massive Bayan Obo Bastnäsite deposits in the Inner Mongolia, together accounting for approximately 60% of global production. China's dominance is even more pronounced in heavy rare earths, where its IAC deposits supply approximately 70% of the global HRE output with no short-term substitute available elsewhere. The USA has the Mountain Pass Bastnäsite deposit in California, operated by MP Materials, but currently still sends most concentrate to China for separation. Australia's Mount Weld deposit, operated by Lynas Rare Earth, is the highest grade bastnäsite deposit outside China and one of only two non-Chinese operations with meaningful separation capability. India has extensive monazite deposits along both coastlines, among the world's largest reserves, but production is tightly restricted, as covered on slide 5. Brazil has significant monazite deposits in Minas Gerais. The critical point is that China's four southern provinces, Jiangxi, Fujian, Guangdong, and Yunnan, supply approximately 70% of the world's heavy rare earths. There is no commercially operating IAC deposits outside China. For DY and TV specifically, this geographic concentration is an unresolved structural vulnerability in every Western supply chain. Now we'll talk about the primary ores. The ore type is the most important determinant of commercial profile, even before grade, location, or magnet or management quality. Bastnäsite is the global industry standard, grading 5 to 9% total rare earth oxide with well understood processing chemistry. Major deposits are Bayan Obo in China and Mountain Pass in the USA. The limitation is a lower basket value dominated by cerium and lanthanum, which are low-value elements. Monazite contains primarily light rare earths with moderate HRE content, but its defining characteristic is thorium, a radioactive element that makes heavy processing heavily regulated across almost every jurisdiction. Despite enormous reserves in India, Australia, and Brazil, Commercialization is significantly constrained. Overall profile is that it's moderate with the regulatory environment as the key variable. Xenotime is very heavily dominated by heavy rare earths, giving it the highest value basket of any primary ore type. The constraint is scarcity. It is primarily recovered as a byproduct of tin mining, especially in the Malaysia, and the global resource base is thin. Ion adsorption clay has the lowest grade of all primary sources, just 0.05 to almost 0.2% TREO, but has moderate to high HRE concentration and the lowest processing complexity in any source. REEs are absorbed onto clay particles rather than locked inside mineral crystal structures, so they can be extracted through simple in situ leaching. No crushing, no flotation, and no high temperature roasting. This eliminates the most capital intensive steps, making IAC commercially the most strategically critical ore type in the world despite its ultra low grade. In summary, capex run high for Bastnäsite and Monazite, medium for Xenotime, and low for IAC. HRE value runs low for Bastnäsite, medium for Monazite, very high for Xenotime, and high for IAC. But supply independence for IAC is very low because it is almost entirely a Chinese asset. Now we'll talk about India's coastal mineral sand. India is the most instructive case study in the RE sector, a country with world-class reserves that produces almost nothing. Understanding why is critical for anyone following the supply chain diversification story. India holds approximately 6.9 million tons of REO reserve, making it the sixth largest holder globally. Monazite sand reserves are estimated at 11 to 12 million tons, and India holds approximately 25% of the world's known thorium reserves, both an asset and the central constraint. Major deposits run along both coastlines. Kerala has the Chavara and Manavalakuruchi deposits actively mined by IREL. Tamil Nadu has the Tuticorin deposits operated jointly by IREL and Tamil. Odisha and Andhra Pradesh hold the largest undeveloped coastal deposit. All production runs through a single entity, IREL, which is India Rare Earths Limited, the sole license operator for monazite processing. Four regulatory constraints explain the gap. First, thorium's classification as a pre-described substance under the Atomic Energy Act of 1948 requires clearance from the Atomic Energy Regulatory Board and the Department of Atomic Energy, creating a structural government monopoly. Second, IRA's monopoly means no private company can legally process monazite without special government approval. Third, ARB radioactivity licensing adds time and compliance cost. Fourth, coastal environment clearance adds a further approval layer. Reform is real, but it's slow. The 2023 Critical Minerals Mission formally acknowledged monazite's RE potential for the first time, and 2025 saw the beginning of a review on limited private participation in separation. The core barriers, however, remain in place. Now we will go over the secondary REE sources overview. Secondary sources generate significant excitement in policy circles. But this slide provides a rigorous, unsentimental assessment of each. Red mud from aluminium production, approximately 150 million tons per year at 0.05 to 0.2% TREO. High alkaline, requiring acid neutralization that drives reagent costs very high. Its viability is low. Fly ash from coal power plants, approximately 1 billion tons per year at just 0.01 to 0.06% TREO, which is extremely low grade with selective leaching at industrial scale still immature. Viability is very low. Coal mine waste, multi-billion ton stockpiles at 0.01 to 0.1% total rare earth oxide, suffers from highly variable concentration by site, dispersed geography, and acid mine drainage complications. Its viability is also low. The phosphogypsum, which is approximately 300 million tons per year at 0.01 to 0.05% TREO, is contaminated with radium 226 and uranium 238, creating severe regulatory complications in most Western jurisdictions. Its viability is also very low. Mine tailings are site-specific at 0.01 to 0.5% total rare earth oxide. Historical processing may have already depleted the most recoverable fraction. Its viability is also low. And the e-waste and the magnet scrap stands completely apart. NDFEB scrap from the end-of-life EV motors, wind turbines, and electronics runs at 20 to 30% rare earth oxide, which is the primary grade material. The challenges are the collection logistics, automated disassembly, and mixed material contamination, which are the engineering problems, not fundamental chemistry barriers. Its viability is very high. This also comes with a warning. Low concentration plus massive tonnage does not equal commercial viability. Every secondary source claim must pass four filters: grade sufficiency, selective extraction capability, separation access, and market price above full total cost of production. Now we will talk about the magnet recycling specifically, which is the urban mine. Magnet recycling is the one secondary REE pathway with a credible near-term commercial case. NDFEB EV scrap has REO content of 20 to 30%, comparative with primary mine ore on content quality. The recycling supply chain runs through seven stages: EV and wind turbine retirement, collection logistics, automated disassembly, hydrogen decryptation. The recycling supply chain runs through seven stages: EV and wind turbine retirement, collection logistics, automated disassembly, hydrogen decryptation or acid leaching, solvent extraction or ion exchange separation to recover industrial oxides, which are NdPr, DY, and Tb, and back into the new NDFE magnet production. The commercial landscape is already active. REE Tech in Norway, Cyclic Minerals in Canada and the UK, Ionic Technologies in the USA, Solvay in Belgium, and Shin-Etsu and Tdige in Japan are all working at technology readiness levels 7 to 9, pilot and commercial stage operation, not early research. The key barrier here are the collection logistics and automated disassembly at scale, which is broadly expected to be solvable by the early 2030s when the first wave of EV traction motors and wind turbine generators will begin reaching end of life in meaningful volume. That timing convergence is one of the more important structural dynamics in the REE space over the next decade. Now we will go over the economic viability framework. Four factors determine whether any REE source can become a commercial operation. This is the minimum due diligence checklist before accepting any project's economic claims. Factor 1: grade and scale. For hard rock, the minimum threshold is 5% TREO. IAC is the exception, viable at 0.05% TREO because in situ leaching eliminates capital-intensive processing steps. On scale, a project must typically sustain approximately 10,000 tons TREO per year to justify a standalone separation plant. The factor 2 is the beneficiation complexity. IAC bypasses beneficiation entirely. Leach solution goes directly to precipitation, skipping flotation and roast. Hard rock processing runs USD 20 to 80 per ton of ore. This is where IAC's cost advantage becomes decisive. The third factor is the separation infrastructure. Approximately 90 to 95% of global RE separation capacity is in China. Without access through a company's own facility or a tolling arrangement, a miner is selling mixed REO at a fraction of separated oxide value. Separation access is a revenue enabler, not merely a cost. The fourth factor is the market price versus total cost of production. Reference price range from USD 1 to 3 per kilogram for light REs, USD 50 to 90 for NdPr, 300 to 400 for dysprosium, and 800 to $1,500 for terbium. The blended basket price must exceed full TOCOP, which is total cost of production, including sustaining capital, royalties, and cost of capital. The structural mismatch is that the energy transition demand is HRE driven, dysprosium and terbium for EV motors, but most investment capital is flowing into LRE dominant Bastnäsite deposit. Heavy rare earth elements rich sources like Xenotime and IAC carry structural price support for the next 10 to 15 years. Now we will talk about the environmental and regulatory challenge. Compliance is not a footnote in RE project analysis. For many projects, it is the primary risk that determines whether a project can be built at all. The four main environmental challenges categories are radioactivity from thorium and uranium, particularly in monazite, acid mine drainage, especially severe in IAC operations, tailings storage facility management for hard rock operations, and chemical effluent from solvent extraction. Key risks highlight: monazite carries critical radioactivity risk, the thorium problem that constrains India's production. IAC carries critical risk for acid mine drainage and chemical effluent. Ammonium sulfate leaching has caused significant groundwater contamination in China's southern provinces, driving tighter MEP regulations since 2006. E-waste has negligible radioactivity risk and no tailing. The regulatory landscape by every jurisdiction. India's AERB and Atomic Energy Act create a critical barrier. The USA requires multi-year NEPA review plus NRC and EPA approval, a high barrier. The Europe's 2024 Critical Raw Minerals Act include accelerated permitting provisions for critical minerals. China's MEP regulations have tightened since 2016, and Australia operates under ARPANSA and the APBC Act, the ESG signal for investors. Rising compliance requirements are increasingly a competitive advantage for clean credential producers. The EU battery regulation, US IRA domestic content rules, and institutional ESG screening are creating supply chain preference for transparent, environmentally credible producers. Compliance cost is becoming a market differentiator. Now we'll talk about the Chapter 2's entire intelligence summary. So there are 8 principles which should anchor every source level analysis in this sector. These are structural logic of how the market actually works. Principle 1, source type determines strategic profile. Bastnäsite equals LRE exposure at $10 to $15 per kilogram basket value. Xenotime and ISA equals HRE exposure at $50 to $200 or more per kilogram. Identify the ore type before any other analysis. Principle 2. The HRE strategic premium is structural, not speculative. EV motors and wind turbine demand for dysprosium and terbium is locked by engineering decisions that will not reverse for 20 plus years. There is no commercial scale substitute for dysprosium in high temperature NdFeB magnet. Principle 3. Ion adsorption clay is China's irreplaceable HREE asset. No outside China ISA deposits exist at commercial scale. HRE supply is structurally China dependent for a minimum of a decade, regardless of how much capital flows into Western REE projects. Principle 4. Monazite's thorium barrier is political, not physical. Thorium has established handling protocols. The barrier in India, Brazil, and elsewhere is regulatory philosophy, and that can change. India's 2023 Critical Minerals Mission is the first sign of that evolution. Principle 5. India's RE gap is a political design, not geology. India produces less than 1% of its reserve potential in RE terms. The Atomic Energy Act and IREL monopoly are the constraints. A policy change could unlock supply far faster than a new mining development cycle. Principle 6. Secondary sources require the four-factor filter: grade sufficiency, selective extraction capability, separation access, and market price above full TCO. All four must be satisfied. Fly ash extraction costs $200 to $500 per kilogram of TREO against a market price of 1 to 100 per kilogram. The arithmetic does not work. Principle 7. Magnet recycling is the only proven secondary pathway. NdFeB scrap at 20 to 30% rare earth oxide is categorically different from every other secondary source. Multiple companies are at TRL 7 to 9 globally. The constraint is collection, logistics, and disassembly, broadly expected to be solvable by 2030. Principle 8. Separation access is the true supply chain choke point. China controls approximately 90% of the global RE separation capacity. New deposits do not solve supply chain security if ore still goes to China for separation. Only Lynas and MP Materials currently operate significant non-Chinese separation capacity. Supply chain independence requires separation infrastructure investment, not just new mines. In rare earths, geology is the starting point. Economics, regulation, and geopolitics remain who actually produces. That was all from my side. If you have any feedback, please make sure to leave them in the comment. Thank you.